Uh, Welcome to this video. This is the module 5 of this series, where we are building a simulated mobile robot. It's a two-wheeled differential drive robot. And in the previous modules, we saw how to build the mechanical part of it, the chassis, wheels, etc. And then we learned how to move around this robot. That means how to make this robot move by giving velocity command to its wheels, and making use of Gazebo ROS plugin. All those things we learned. Then we learned about how to add sensors like camera, laser to the robot itself, so that it can see the world. Then we learned how to use ROS navigation stack to build map using G mapping, and then use AMCL localization algorithm for autonomous navigation. Now in this section, we'll see how do we write our own motion planner. That means we'll write our own nodes that will publish and subscribe things. That means you want to read the sensor data and write your algorithm, and this algorithm will make the robot respond to the environment in a particular way. That means you can write your own motion planner, you can implement your own algorithms. So this is what we'll see in this section. So to this I am assuming that you already know how to write your own programs for publisher and subscriber nodes. And so if you haven't gone through, it will be good to go through this link that explains this topic. For example, if I click here, it tells you how to publish and subscribe using Python. I'll be using Python for my program. So this page describes how to create publisher node and subscriber node using Python. To save time, you can download the codes directly from a repository. Use this command and use the branch motion. So -b motion is important. So that has all the files necessary for this module, to understanding this module. Once you download this source code inside the catkin underscore workspace and src folder, you can run catkin make to build the whole thing. And also I assume that you have completed the other parts of the series up till now, so that we are ready with the robot and things like that. All right. So what we do is that inside our catkin workspace src escapeboard folder, we create a new package called escapeboard motion, and this escapeboard motion depends on ROS-Py, standard messages and geometry messages, these other ROS packages, and sensor messages. So you'll have to use this command, catkin create package escapeboard motion, ROS-Py, standard message, geometry message, sensor message. That means this particular package depends on all these other packages. Now inside the escapeboard motion, we now create a folder called scripts, and we first create a file called reading underscore laser.py. We'll talk about the content of this file. This is basically a publisher node. That means if you run it, then it publishes data on a particular node which you can view and stream. We give a executable permission to this file, chmod a+x. This is a standard way to give executable rights, and then we can build this whole thing by running catkin make and sourcing the updating the ROS tree by running this command. Now if you see the file reading underscore laser dot py, it is nothing but a file to publish the data. So what it does, it has a callback function. Okay, so it takes the data type MSG. MSG is a sensor message type, and we import the laser scan module, and this it has 720 data points. So we divide into 5 regions, and for each region we are just printing the value between 0 and 10. That means we discard any value beyond 10, because it doesn't make sense to if the obstacle is very far away. So we just display the data between 0 to 10, and we divide the data into 5 regions, and we show the minimum of 0 to 10. And this is a function, and once these regions are then published to the log info, that means according to log info, then we have this main function that creates this node called reading laser, and then this is a subscriber node that subscribe to this topic escape laser scan and reads the data from it using the and this callback laser function is used to process the data that we read from the scan. Alright, and once we have done that, now we create a custom world, because we need to have a little more complex environment to make use of this data. Our purpose is to make the robot move autonomously while avoiding obstacles. So for that we want to have a little complex world. So this escape custom world is provided in the world folder. So what we do is we just make changes to the escape world.launch and make it to load this escape custom.world file. Okay, so here I don't talk about how to create this custom world. Just to give a summary, what you do is that you open a empty Gazebo world, and then use the insert tool in the menu to load various components, okay, pre-existing Gazebo components, and finally you save it as a word file. Okay, that word file can be now included in the launch escape launch file. Alright, so once you have done that, that means once you have created the reading laser subscriber node program, and loading a creating a custom world file, then you are ready to launch these two commands. One is the world file itself, another is the we are running the subscriber node. Alright, and then you should be able to see this is our world environment. There are many obstacles are there, and robot is somewhere here, and these blue lines are the readings from the laser scan, and if you subscribe to it, you can see the data something like that. The last 5 data are the minimum value between 0 to 10 for 5 regions. So let's see how it looks. So we go to our Catkin workspace, and if we do ROS cd skbot motion, I have already built this folder. That means it has been compiled using Catkin make, and ROS tree is updated. So if I go to scripts, now we see now gvim reading laser.py. So what you see is that it imports this module ROS.py sensor messages dot message import laser scan, and this is the callback function that processes the laser data which is available in the form of variable MSG, and these regions are then recorded or maybe the published back. Alright, Then we create a subscriber node called reading underscore laser. Ross by subscriber is the tells that now subscribe to this particular topic keyboard laser scan and process this data using the callback function. And then we have the rospy dot spin, which makes it check repeatedly within the loop. And in the main part we just call this main function. Now let us see the you know raw cd gazebo gazebo cd worlds. We create a custom world.stf, and as I told you, it is easy. Just to show you how you can do it, I do gazebo custom world.stf. So what you can see, this is our world that we built. So the idea is simple. You go to this insert part, and a lot of models are available here. Actually these there is a lot of models are available, and you can just drag and drop these modules. For example, I can cabinet, I can bring it here and put it here, so on. You can put all these things and put it in right position, and then probably file save world as, you can save this the whole configuration as one file called .stf, save configurations, and then save world as summary you give, and let's say SDF file. It creates SDF file, and you can rename that SDF file as the world file. For example, this is our custom world.sdf. We just rename it to say skboard custom.world, and now we go to the launch file, cd launch folder, gvim skboard.world.launch. So in this one you can see I am loading the empty world, and then I am loading the skboard custom world. You can have if you remember on previous modules, we launched Turtlebot, Playground, and skboard.world. So in this one we will use the skboard custom.world, which we created for this module. Now everything seems to be in place, so we can now launch ROS launch skboard gazebo skboard world.launch. Okay, and in the other module we say ROS run skboard motion, and we run the reading laser.py. So you can see the data is being published continuously, and the last 5 data are the minimum value laser readings for 5 regions between 0 to 10. Okay, and if you want to see the world, you can see that it is seeing the various obstacles. Okay, so the readings will change if I make the robot move. For example, if I make the robot closer to this wall and then check the data, probably this part is 1.7. the first two first 3, in the middle 3 are little less, 1.7, 1.6, 1.8, because it's close to the while in the this side it is more. So it is obvious, because these 3 sides, this side and this front side, is very close, while on this side it is quite large. Okay, so this is all right now, so we'll just turn it off. So we completed this part. Now what we'll do is that we'll create another script called obstacle avoidance .py inside this script folder. Here we implement the obstacle avoidance algorithm using the laser data. Alright, and as usual we give the executable permission to this script file. Once is there, we can run these two commands to make the robot move. So before we go, let's see the content of this file. Here we load not only sensor messages but also the geometry messages. The geometry message is used for giving the command to the robot, which is of geometry message / twist type, while the sensor message is used for reading the laser scan. So we define a publisher which is a public variable, that is a global variable. Alright, and this callback function not only processes the laser scan data, that means it divides the laser scan data which is of dimension 720 cross 1 into 5 regions, and then these regions are then used to check obstacles and take actions. So the callback functions also takes actions. So take action is another function which produces a message of type twist. So what it does is that it checks all the 5 regions whether the obstacle is there or not, and accordingly it decides the motion of the robot in a linear X. Basically we need two kinds of motion. One is the whether we should go to forward, that is called linear velocity X, or you should rotate, that means you give a angular motion around the Z axis. So if the obstacle is there, we give a motion around the Z axis and the forward motion is stopped. So there are several cases, 8 to 9 cases will be there, and all these cases we mention using if and else if statement, and ultimately these messages, the states and the messages are recorded somewhere. So we we provide some name, state description, and the messages, the linear velocity and angular velocity is mentioned, and this is published using the publisher command. Now if you see the main function, so it updates the public node POB, it creates a subscriber node reading laser. So the publisher publishes this velocity command that we created in the take action function to SKBoard CMD well, and then subscriber reads from this laser scan and uses callback laser. Note that the callback laser reads the data, processes the laser scan data, and then create message type which is published to CMD well. So with single callback function we are achieving both the task. So if we see now, so if we now see here, so what we do, we start our robot once again. Okay, we launch our custom world, and in the another terminal we, instead of reading laser, we run the obstacle avoidance.py algorithm. So as you can see now, you can see that the robot is moving. Okay, and it is successfully avoiding the obstacle. Whenever it is coming across a obstacle, it is changing its orientation, that means it rotates around the Z axis, keeps on doing until it finds a empty space to move around. As this behavior can be utilized to generate the map autonomously. If you remember in our last session, we were moving the robot through teleoperation, the keyboard movement, and sometimes it is time consuming, because if you have a large environment you'll have to go around obstacles, all the obstacles, and get the scan. But now with this kind of algorithm, it is very easy to autonomously build the map. Alright, so this is also possible. So we'll stop it here. um, so I have provided these commands. If you run these commands, for example, in the first terminal you launch the custom world that we created, and in the second terminal you run the gmapping demo launch, already using the SKBoard navigation package, and then you can launch a RViz file where you can add robot model, laser scan, and map to the display window, and in the fourth terminal you run the obstacle avoidance algorithm. So what will you see that robots moves on its own the environment, and in the process it builds the entire map. And once the map is built, again you can use AMCL package to for autonomous navigation. So these are explained in the previous modules, so I will not explain it here. So to summarize, we learn in this video how to create our own programs, nodes to control the robot motion and process the sensor data. So this can be used for developing and implementing new algorithms on the robot, and then we demonstrate how to implement a obstacle avoidance algorithm. You can take it as an exercise to build a wall falling robot. Lot of code is available, a good tutorial is available on this page where it explains how to do all these things, so you can refer to this part and build your own algorithms. Thank you for your time. Goodbye.